Now we start this topic today. It is about what is your, this three terms are there: substantial derivative, local derivative and convective derivative. Now these terms will come quite often in our study or calculations, so we should be very clear that what they are. Okay? So they form the first basic thing about CFD. Okay, so what we are talking about is, there is a formula like this, derivation of so what we are talking about is d rho by dt is equal to del rho by del t, and this is the divergence of rho multiplied by velocity vector. Okay, what does this actually mean? Okay, so we are going to derive this equation first, and what we are doing is, we are considering a very small, infinitely small fluid element. So our fluid element is very small, which we are considering. Now then the important thing is that with the impervious boundaries. So our element is sort of having boundaries which are impervious. That means no fluid can come in or no fluid can go out of that space. Okay, there are two types of, you can say, formulation, in which one is the impervious boundaries, the second is open boundaries. So you can also derive formulae hoping that with the idea that your boundaries are open. Okay, in that case the fluid comes in and goes out. But here what we are considering, that the boundaries are impervious, or you can say closed, but the boundaries are not, you can say, rigid. Boundaries are flexible but impervious. So you have to see the difference between them. Suppose you have a thing like this, you have an element like this, like nothing can come in and nothing can go out, but as it moves it can change its shape. It is the same element, but it has changed its shape. Whatever the fluid was here, the same fluid is there in this new boundary, but the shape has changed. Okay, so this is what we are talking about now. And then we have a flow field which is non-steady, okay, and non-uniform. So these are also two important terms we should remember, that the flow field which we are talking about is non-steady and non-uniform. Non-steady means the parameters, the flow parameters, they vary with time. Steady is the term which is associated with time. Something which is not changing with time, you call it as steady. Okay, so it is non-steady. That means flow parameters are changing with time. At any point the velocities, densities, pressure, they are changing. Then the second thing is non-uniform, means uniformity is with space. Okay, that the flow parameters vary with position. That means we are not saying that the parameter is fixed with respect to space. Okay, and I can just elaborate it here. Suppose we are talking about something which is steady, steady and non-steady. We are talking about steady or non-steady. If you want to put it mathematically, then if you have a parameter del phi by del t, if that is equal to 0, then it is a steady. That means the parameter is not changing with time. If it is not equal to 0, then it is unsteady. Simple. Okay. Now similarly we talk about uniform and non-uniform. Okay. Now if you have a parameter and del phi by del xi, if this is equal to 0, it is uniform. And xi are basically that is a way of writing. Xi are basically x1, x2 and x3, which are also written as x, y, z. So we are talking about 3 dimensions of space. So xi means all the 3 directions. I is can take the value 1, 2, 3. So if del phi by del xi equal to 0 is uniform, and if it is not equal to 0, that it is non-uniform. Okay? So what we are talking about is, so this is what the field is. Now this is our 3-dimensional field, and what is happening is that our fluid element is present at this point at t equal to t1. It follows a path and comes to this point at t equal to t2. Again, it may not have this shape, it can have a shape like this. Okay, we are not concerned about the shape, we are only concerned that nothing is going in and nothing is going out. Okay, so the fluid element is moving. Now, for a non-uniform and unsteady flow, which is a general flow, so steady flow and a uniform flow will be a special case of this. So we are considering a wide one which is catering to all the cases. Now the flow parameters, they will be functions of both space and time. So what are the flow parameters? U, V, W, rho, T, etc. So your 3 velocities, U, V, W, density, temperature, and of course pressure and densities are related by temperature. So pressure, density, temperature, they are related, so we can take any 2 of them. You know the equation, P is equal to rho RT for an ideal gas. Okay, so you need not take all the 3, you can take 2. Okay, then what do you say? That U is basically a function of 4 parameters, x, y, z and t. Similarly V, W, rho and your T, capital T will also be function of all these things. Now then if you say that what is the value of rho at time t1 at point 1, so rho 1 is equal to x1, y1, z1, t1. This is some function. Okay. At later time t2, what is happening? Now you have moved. You are not now at a different location, x2, y2, z2 at time t2. So density there is rho 2. Okay. Now although our fluid element is segregated from the fluid, it is isolated, or you can say closed, but at whatever point it is having the same properties as that of fluid. So because we are considering the fluid only, it's only that we have put an imaginary boundary around it. So actually it is the element, if it is at point 1, it is having the properties which were there at point 1 in the fluid field, and when it comes to point 2, it is having those properties which is which are the properties of the fluid at point 2 at time t2, right? So it's the same fluid, except that we have kept an imaginary boundary around it. Okay. Now if you write Taylor series for this, you already know this. Rho is equal to this. Rho is a function of 4 variables x, y, z and t, and you can use Taylor series to write equation like this, rho 2 and rho 1. What is the difference between rho 2 and rho 1? Okay. So rho 2 will be equal to rho 1, and then you have to multiply rate of change of rho with x1 multiplied by change in x, rate of change of rho with y multiplied by change in y, rate of change of rho with z multiply with change in z, rate of change of rho with time multiply with change in time, and all the higher order terms are put together here. Okay. These higher order terms keep on approaching 0 as your point t2 2 approaches to 1. As if you are very close to point 1, then these higher order terms will be negligible, because then they will be having a higher order, a square of x2 minus x1, square of y2 minus y1, square of z2 minus z1, all that will come in and they will become almost equal to 0. So you can write rho 2 like this, and you can take the rho 1 on this side, you get rho 2 minus rho 1 equal to all this. Okay. And then what you can do, you can divide all this equation by t2 minus t1. Okay. So what do you get? You get rho 2 minus rho 1 by t2 minus t1 is equal to this. So you have x2 minus x1 divided by t2 minus t1, y2 minus y1 divided by t2 minus t1, z2 minus z1 divided by t2 minus t1, and this of course goes away, this t2 minus t1, because you are dividing the whole equation by t2 minus t1. Okay. And now you know you can write it like this, because your t2 is very close to t1, or you can also say that point 2 is very close to t1, all these higher order terms will go equal to 0. Okay, and you get this equation, d rho by dt is equal to u del rho by del x into v del rho by del y, w del rho by del z plus del rho by del t. See that this term is actually velocity u, this is velocity v, and this term is velocity w, u v w. Okay, simple mathematics. I am just communicating to you the idea behind it, the physics behind it, how to understand it. Okay, mathematics, I don't go into very difficult mathematics, because then you lose the sense of what is happening. Okay. Now these three terms can be put together and can be written like this. Again simple. So what we have done, we have only found derivative of rho using Taylor series, right? And then putting the limit that point 2 is approaching to 1, and we get this equation d rho by dt. Okay. Now what are these two terms in this, because we have to understand that what is there. Okay. Now d rho by dt, this term, this represents time rate of change of density of the fluid element at point this. As it moves through the point T1. So this is telling you this term d. This is a total derivative. Okay. This is telling you the total change in density with respect to time. Right? And okay. But this is made of two other terms. Okay, one is this term, the second is this term. Okay, so d rho by dt, this term is telling you the rate of change of density of the fluid element as it moves. But this term d del rho by del t, this is telling you the change in density at the same point with change in time. So you know what does the partial derivative means? Means that all other variables are constant. When you are talking in terms of del t, x, y, z are constant. So what is happening here? x1, x, comma y, comma z, they are constant. What does that mean? That the element is at the same point. So if the element remains at the same point, okay, but still its density would change because the field is changing, field is unsteady. At no point in the field your density is constant, right? So wherever you are, at that point the density is changing. Okay, so we are not bothered whether the point has moved or not. We are actually talking about that at the same point. It's something like like this. If you are standing outside, okay, at a particular point, morning the temperature is different, afternoon the temperature is different, evening the temperature is different, and night again the temperature is different. So you have not changed your location, right? Same place you are standing, but the temperature is changing because it's an unsteady field, right? Similarly, you can have a bucket of water, put your probe there, your water is not moving, your probe is not moving, but with the environment the water temperature will change and you will keep on noting the change. So that is your del rho by del t. Okay. Now, what are these terms? These are called convective derivatives. Okay. They are called convective derivative. Convective derivative means by change, the change because of change in position, not because of change in time. So for these, all these, time is constant. So that means if you are not moving, if you are at the same time, if you keep the time constant, but if you move in the field, what is the change in the density? Take an example. You are again, we come back to the same example. You come standing outside in the atmosphere. Your temperature is different at different points. If you are under the shade, the temperature is different. If you are in the open, the temperature is different. If you are standing against a wall, the temperature is different. So the whole field is having different temperature at different places. And we are talking about the same time. Okay. Of course, you yourself cannot be present at all the places at the same time, but you can have probes. So your probes are at 5 different points, and at the same time you take the temperature, what you will find that each point the temperature is different. And if you move from, because your temperature is same as that of field, we are actually talking about field only. So that element I told you is not separate from the field, it's part of the field. So if you are there, if your element moves from one place to another place without any delay in time, right? Of course that is not possible, you cannot move from one place to another place without it, but just imagine. Then the change in temperature or density or pressure, whatever you will feel, is called convective derivative. That change is because you have changed your location. Okay, so that term comes here, right? So there are two terms, one is called local derivative, the second is called convective derivative. Local and convective, and if you sum it up you get total. Okay, so if you are talking about the total change, there are two things which are making it change. One is the time, and the second is because of its location. So these are, so now we talk about something more about this. What is the physical significance of this del rho by del T, this and this. Okay, so del d rho by dt is called the substantial derivative or total derivative. This is the name given to it, where d is capital or small. You can have both. You can write it as d rho by dt, or you can write it like d rho by dt. Both are same, but it is not same as del rho by del T. So one is a partial derivative, other is a total derivative. Okay, so this substantial derivative or total derivative contains two components. Okay, what are those two components? One is called the local derivative, del rho by d, and what does it represent? The change of density of the fluid at a point with respect to time. So del rho by del T is telling you what? You are standing continuously at a point, then because of the change in with time, the change in rho, it is called as del rho by del T. So this term exists even when the fluid element is stationary, as flow field is not steady. अगर फ्लो फील्ड स्टडी होती तो ये ज़ीरो हो जाता. ठीक है, वी स्टार्टेड विद अ, सो इफ यू del rho by del T, it can be equal to 0, it may not be equal to 0. If your field is steady, then this is the case, it will be equal to 0. If it is non-steady, it will not be equal to 0. Okay, so at the same time, if you are measuring a parameter, if it is changing with time, it is non-steady. If it is changing with time, it is non-steady. Okay, now we talk about convective derivative. This is called convective derivative. Okay, now convective, as the word goes, convection. Convection is movement. You know convective heat transfer. You talk about convection, right? So convective heat transfer is the heat transfer because of the flow of the medium. You must have learned about those examples. There is, when people are exchanging your 10th class or 9th class example is there, where two people are exchanging balls, right? Or there are many people, right? And we can just take that, because that would make things somewhat clear. Suppose many balls, okay? These are the atoms. If your heat is flowing like this is conduction. If your heat is flowing like this, it is convection. ठीक है? इसमें corresponding जो होगा, what will happen? The cold will come here. And if your ball is going like this, jumping, right? It is a radiation. Okay, so we are talking about this convection, where you actually move. Okay, so what we are talking about here is convective derivative. So it represents the rate of change of density of the fluid element due to change in position in the flow field. So because you are changing your position, that is why this is changing. And remember, while changing the position, we are not talking about change in time. What does that mean is, you are simultaneously taking the value at two different locations. Because if the same probe is there, then you have to travel. It will take time. But if you put two probes, right, so you can take the reading at 2 points simultaneously. Okay, that you can do. Now this term is non-zero as the flow field is non-uniform. That means if the flow field is not changing with space, then this term will be zero, otherwise it will be, right? So you should remember that a field can be uniform but non-steady. A field can be steady but non-uniform, right? All things can happen. And a field can be both uniform and steady, and a field can be both non-steady and non-uniform. Okay, non-steady and non-uniform is general. Suppose we talk about a field, and what a field which is steady as well as uniform means that no change is taking place. Everywhere the same. So if suppose the temperature is same in the room, morning also, afternoon also, evening also, at every point it is same. So the field is uniform as well as steady. But you can have a field which is, let us talk about a field which is steady but non-uniform. What does that mean? That the temperature is not changing. It's same, morning also same, evening. But at each point the temperature is different. Okay? Somewhere the temperature is more, somewhere the temperature is less. Other side, that it is uniform but non-steady. That means if it's like a bucket of water, you are heating it up, its temperature is rising, but everywhere the temperature is same. You are stirring it also. So wherever you put the probe, temperature is same. But after 1 minute, after 5 minutes, after 10 minutes, the temperature is different. But it is same at all the points. So that is you have a non-steady but uniform. Same everywhere, but it is changing with time. Okay. Now, so your field, when your field is non-uniform, gradient is there. Now how do we find it? This is the product of velocity of the element field and the gradient of density. So it's basically product of two things, velocity and gradient of rho. For any parameter, if you have some other parameter, it is always, you can write general. Okay, now what is gradient? Gradient is, we have already written here, this term is local derivative, this term is convective derivative. Okay, now what is gradient? Now gradient is the rate of change of a quantity with respect to distance. That is called gradient. Okay, for an example, gradient is a slope of a road. We normally talk about the gradient is high, gradient is low, gradient is negative. When you talk about roads or roads on the hill area or railway line, gradient becomes important. That how the height is changing as you move along the road. So gradient means if your height is changing faster, then it is a steeper gradient. If it is flat, it's a zero gradient. If it is negative, that means your height is going down as you are moving, it is a negative gradient. And when you design the roads, you take a precaution that you cannot go beyond a certain gradient. And that is the reason why on the hills the roads are circular. Because if you want to reach the top, you cannot climb the gradient, or your vehicle cannot climb the gradient if you put a straight road from bottom till the top. It may be 40 degree, 50 degree angle, you cannot climb. So what do? You make the roads in a circular path. What you are actually doing? You are reducing the gradient. You are increasing the length and rate of change of height is reduced, right? So that is called the gradient. And now you translate this into any other parameter. The gradient of temperature means the change of temperature as you move in x direction or in y direction. So in this room also you find a gradient. Now your bottom may be colder, the top may be hot. Normally, if you are living in a room which is unconditioned, you will find that the roof is open to the sky, or it is, what will happen? The top is hot, the bottom is, there is a temperature gradient from bottom till the top. It is changing with distance, right? So this is what is gradient. Gradient is measured in three space direction. It can be in all the three directions. Same thing, you come to the room, you have windows. The temperature near the window will be higher. As you move away from the window, it will be colder. So there is a gradient as per the direction. If you have a heater here put in a room, as you go away from the heater, you will find the temperature is lower. That is a gradient. Okay. So as you move along the direction, the change in temperature, or for that matter any other parameter, will be called the gradient of that parameter. Now when you multiply that by velocity, it gives you the rate of change with respect to time. But change because of movement, not because the field has changed. Okay, remember, the gradient is telling you what? That what is the change because of change in location with the time, because all derivatives are with respect. But this change is not because of time, it is because of location. So when you are moving from one point to another point, there are two types of changing taking place. One, because the temperature there itself has changed, and the second is because you have moved from a colder region to a hotter region, so the temperature has changed because you have moved from one region to another region. So there are two different changes are there, right? One is a convective, one is local. Okay, so this is the formula for gradient. You must have come across gradient. Okay, and phi can be any quantity, density, temperature, and for all the scalar parameters you can have gradient, and even for vector parameters you can have gradient, right? For a vector there will be 3 gradients, so there will be total 9 terms, because what happens if you have a if you find a gradient of phi, it gives you 3 terms, right? Del phi by del x, comma del phi by del y, comma del phi by del z. But if you talk about a vector, you can find the gradient of a vector. Now it will have 3 into 3 components, del u by del x, del v by del x, and del w by del x, and so on. Okay, so don't think that you cannot find the gradient of a vector. It can be there. Okay. Okay. Now then we talk about the examples of substantial, local, and convective derivatives. Now, just a practical example so that it becomes more clear. You take an imaginary balloon. So what you have done is, there is a balloon. It's an imaginary balloon. Why we take a balloon? Because impervious boundaries. Nothing is going in and nothing is going out. But of course, this balloon is in equilibrium with the field, in the sense that it is having the same temperature and pressure what is around it. It's a small balloon. Okay. Now, as this balloon moves in a river, what happens? Its temperature would change. Suppose that water balloon is there, it is changing is moving with the river. Or there is another balloon, let's take example, which is moving in an atmosphere. Okay. So the rate of change of temperature of the balloon with respect to time is total derivative. If you are finding what is the change in temperature with time, it is the total derivative. But the rate of the change of temperature of balloon with respect to time is total derivative. The rate of change of temperature of balloon, if it had remained at the same location, you can hold that balloon there and the river is flowing. Or you hold that balloon in the atmosphere at a particular position. Okay? So what will happen? That is a local derivative. Its temperature would still change. That is a local derivative. Now then the rate of change of temperature of the balloon due to change in its position. Now what happens is, suppose you quickly move balloon from one position to another. So you are at the same time from here to here. Then again, because at the downstream the temperature is different, the balloon temperature has changed. So that change is because of the convective derivative. Okay. Same thing you can talk about air. Let me not repeat it. Then there is a good example of hiking in mountains. Suppose you have gone to mountains for a tourism with one of your friend. Now you are walking on the way, you are near the snow is all around you. Okay, you are standing close to a cave, right? Now you start moving inside the cave. Okay. Now outside temperature will be different than the inside temperature. Cave temperature will be different. It will be higher than the what is outside, because it's all cold outside, right? So as you are moving in the cave, the change in temperature is convective derivative. But let us suppose at the same time that your friend hits a ball of snow at you. Now that ball lands on you and it cools you, right? That is your local derivative. The change, local change, right? There was one change because you were moving. There was one change because you are standing at a point, right? And the total change will be because of both. Okay, so that is the net temperature drop you feel as you walk through the mouth of the cave, therefore is a combination of both the act of moving into the cave where it is cooler and being struck by a snowball at the same time. So the effect will be, both the effect will be. The rate of change in temperature of the balloon with respect to time is total derivative. When you are talking about the balloon as a whole and you are not considering about its position, whatever the position is, T1 and T2, alright, wherever it is, at T1 it is some point, T2 at it is some other point. So the change in temperature, that is total derivative.
So means we are not considering its location.
No, we are not
considered to be as uniform.
No.
So we are not considering location, then why it cannot be uniform?
No, now we are focused on the ball. Wherever the ball is, we are not bothered what is the location and what is the time. We only know that time T1 the temperature is this one, time T2 the temperature is this. So this is the total derivative. What you are actually, whenever you will measure the ball, you will actually measure the total derivative. वो तो हम मैथमेटिक्स में उसको ब्रेक कर रहे हैं. If you go and measure the temperature, you get the temperature. What temperature? The temperature doesn't measure where you are located and what is the time. Okay. वो तो आप उसमें कोऑर्डिनेट डालेंगे ना बाद में कि that at this time at this location this was the temperature. When you put the thermometer says this is the temperature of the ball, that's all. So that is total derivative. Now you break it into two parts, that if I would have moved this ball from A position, location A to location B in a instantaneously, so what would have happened? मेरा जो temperature था from A to B, its temperature is changed. Not because time has changed, because my location has changed. That is convective derivative. But in real life, when you move from point A to point B, your time has also changed. So there is one more change, that when you reach point B, your time has also changed. What is that change because of the time? So that will be your local derivative. Okay. Although that local derivative occurs, if you find, so when you are finding the, let me see that if I can draw that diagram. Okay. Now when I move from point 1 to point 2, okay, and it is, let us say, time, this is also time T1, this is also time T1. This change in temperature is convective because of the movement. Okay. Now from here to here I move point time 2. Now I change the time T2 to T3. This change is local. Okay. This change is convective. But when I am talking real life, I am talking about this temperature change. It has both the components, the because of distance as well as because of time. Now the problem is that you have split it in two parts, but these two things are happening simultaneously. You are changing your position as well as the time is changing. So बट मैथमेटिक्स में हमने क्या किया, उसको दो पार्ट्स में डिवाइड कर दिया और हायर ऑर्डर टर्म्स हमने छोड़ दिया. हमने कहा कि ये इसका चेंज और इसका चेंज जब आप ऐड करेंगे ना तो इस चेंज के बराबर नहीं होगा. बट द ऑर्डर विल बी वेरी स्मॉल एंड बाय मेकिंग दिस पॉइंट वेरी क्लोज टू दिस पॉइंट, राइट, यू इग्नोर दैट. मतलब वो मैथमेटिकल ट्रिक है. ठीक है. सो इवन इफ यू ऐड द convective derivative, convective change and the local change together, it will not be the real change, because local you are measuring either at point 1 or at point 2. But the point, actually the ball has moved from 1 to 2, so the local was changing all the time, the convective was also changing all the time. And when you move from point A to point B or 1 to 2, you don't do instantaneously. So whatever the change is also not the convective, but it is a way of representation it, that what is the effect. We have to, because the real life, time and space are changing simultaneously, right? We are just breaking them in mathematics to understand it properly, so that is, we know what is the impact of this. Okay, तो ये है. तो can we stop here?